All right, guys. Thank you very much for the organizers for inviting me. It was kind of very fresh for me to get out of the Van der Waals community and to see other people. So it's a great pleasure. And today I want to share with you our recent work about the nonlinear transport in graphene-based superlattices. Before I go to my results, let me introduce my collaborators and colleagues with whom I worked over many years to understand and study nonlinear transport in many graphene-based systems. First of all, it is Andre Geim, and this work mainly have been done during my time in Manchester. Then Xin, who is very talented nano-fabrication person, and Roshan Krishna Kumar, with whom we have designed and studied those experiments together. All right. By the end of my talk, I want to show you something different from what you have seen today and give some feeling about space-related physics. And today I want to convince you to show you that the Schwinger-like particle electron-hole creation is actually the main process which dominates the high bias response of all graphene-based superlattices. Okay, let me introduce the systems with which we have worked for this. Okay, sorry. Okay, the main system which we use is two types of the superlattices. First one is graphene aligned with hexagonal bornitride, and another one twisted bilayer graphene. I'm sure that many of you have heard about those systems, but in case if somebody didn't, because it's quite a diverse community here, let me tell you that in those samples, aligning of graphene with hexagonal bornitride or twisting two graphene layers creates so-called Moiré superlattice, which you can see here. That is additional spatial periodicity, which reduces the size of the brilliant zone in K-space and gives the origin of the mini band structure, which you can see here. And as a result, in those devices, if you make them and align them properly, you can see you can tune the Fermi level just through the entire energy band structure and observe even secondary neutrality points. And up to this point, people have been studying those systems quite a lot and have observed a lot of interesting electronic phenomena there. Historically, people discovered first graphene aligned with HBM superlattices. And in those structures, they have been studying half-stator butterflies, the very beautiful quantum fractal which appears in those structures under applied magnetic field, and also getting glimpse of topological physics by observing topological currents via non-local measurements. And the twisted bilayer graphene is relatively new to the graphene HBM superlattice, and which became popular around 2018 when group in MIT have first observed the superconductivity and correlated insulators in so-called magic angle twisted bilayer graphene. And later on, people have observed orbital ferromagnetism, strange metal states, and much more. Very, very rich many-body phase diagrams there. But what is missing up to this point that people in all those experiments have been using extremely small currents, like in order from 1 to 100 nanoamp to measure those devices. And that is mainly done for two reasons. First reason is just people are extremely cautious. When you get the good device which gives you beautiful data in a linear response regime, you really don't want to mess it up, yes? And that's why you're cautious and apply extremely small excitation current to keep it safe. And another reason is a little bit more trivial. People just don't believe that something interesting can come up if you increase the excitation current. That is for the reason that typically currents viewed as just a source of heating. And you apply larger current, you heat up your sample, and you don't observe any interesting quantum effects anymore. And that's why people don't really do it. But at some point, we decided that we want to do something silly, something stupid, and decided to bias our samples a little bit more. But in reality, we also had some other motivation in our mind, which was coming from the previous experience of people with one-dimensional superlattices. And the research on one-dimensional superlattices, like in the 70s, were pioneered by the Leo Isaki, who was studying the vertical superlattices made of gallium arsenide two-dimensional electron gases. And in those structures, he was looking for so-called Bloch oscillations. and which is very interesting and unusual, very counterintuitive phenomenon. If you apply the DC bias to your superlattices, then if you induce the ballistic motion of electrons, you can observe that it goes ballistically through the entire Brillouin zone and even go to the next zone. But it actually means that mathematically it's equivalent to the process that it just jumps to the opposite side of your Brillouin zone. And so this periodic motion of electron in K-space actually corresponds to the localization of electron in a real space. And it starts to oscillate in real space and don't go anywhere, despite you applied just constant electric field. And in experiments with those superlattices, people indeed have observed something interesting and some negative differential resistance and signatures of irradiation. But I will not comment on how those features actually, if they well connected to the Bloch oscillations, but it gave us the feeling that something interesting might came up if you will start biasing the superlattices. All right, let me move to our experiments. Our experiments actually are super simple. Like, I'm sure that everyone with proper graphene devices can do it. To study the nonlinear transport, you simply just need to take conventional whole bar and apply current. That's all you need. And to begin with, we studied and characterized our whole bars in a linear response regime and see that they're indeed completely usual. We see if we measure resistivity as function of carrier density in those devices, we observe the peak at zero carrier density, which correspond to the main neutrality point. And if we tune the carrier density, we also observe satellite peaks, which correspond to the moment when Fermi level crosses the so-called secondary neutrality points. To study nonlinear transport, we simply fix the carrier density and increase current. And the result immediately got our attention for several reasons. With the red color, those plots, you can see the AV curves, and with the blue color and black color, you can see the corresponding differential resistivity, which is simply the derivative of those AV curves. And if you look at this AV curve, it closely resembles a superconducting transition. And perhaps we would not be so surprised to see this kind of superconducting transition in twisted bilayer graphene at that time, because at that time people was hyping up about superconductivity in magic angle graphene, and here we have relatively small angle graphene device. But at that point, it was already well known that graphene aligned with HBN doesn't actually superconduct. And that's why it was super strange, and we didn't really understand what's going on. To gain a little bit more information, we decided to measure. We measured our samples a little bit more. And here you can see the differential resistivity, which is this black line, as a function of carrier density and current in our devices. And with the white arc, you can see the peaks corresponding to the maximum of the differential resistivity. And in those maps, you can see quite a systematic behavior. First of all, you see that this transition happens not at some particular carrier density, but it happens just everywhere. And sometimes we actually get kind of spectroscopic maps. You can even think of it as an RPS in with some stretching. And here you can see that those white arcs, peaks, converge to the zero current around the neutrality points. And it happens around every neutrality point in twisted bilayer graphene and around secondary neutrality point in graphene HBN superlattices. To measure this effect further, we decided to measure the Hall effect to understand if we might see something interesting there. And for this, we simply measure the Hall voltage and measure IV curve of the Hall effect, basically. And the result you can see here. Here you can see the differential resistivity of the Hall effect, and you see quite a good correlation with our longitudinal resistivity measurements. Every time we reach the transition point in our longitudinal resistivity, the Hall effect tends to change its sign. And all this behavior somehow reminded us the tuning of Fermi level across the neutrality point. But in this time, we're doing it not with the carrier density like you usually do, but now somehow you do it with electric field, with in-plane electric field. But for some reason, we still didn't see anything around the main neutrality point of graphene HBM superlattices. And with this in mind, it was rather confusing for us if neutrality point is somehow very important. why we don't see it here. And we decided to investigate it a little bit more and trying to see and bias our devices without superlattice. Okay, in those experiments, we decided to focus on a little bit unconventional geometry. Typically, up to this point before us, people have been studying electron transport in graphene devices for quite some time. And of course, they have measured nonlinear weak curves. But what have been missing is that people didn't really try to squeeze a lot of current into the narrow constriction devices and see the response. While such geometry, in terms of experiment, has its own benefits, that it allows you to avoid overheating of the contacts and to avoid too much of the self-gating in your experiments. And once we apply the current through this very narrow constriction, we see rather similar transition type curves. We see the peaks in differential resistivity and kind of transition in IV curve. And if we measure this process a little bit more systematically, we also see that those peaks in differential resistivity already converge to the main neutrality point, just like we saw in our graphene HBM, in graphene superlattices. But the only difference is that this time the current density is several orders of magnitude larger than what we needed in superlattices. To understand what's going on, we decided to make some estimations. And I should tell you that our other motivation to switch to conventional graphene was relatively simple spectrum in this system, and that people understand the physics of graphene relatively well at this point. And to understand the nonlinear electron transport in graphene, you need to think in terms of the shift of the Fermi surface. Okay, assuming if you have some initial electron doping, and you have electrons moving to the left, to the right, to the up, down, to all the possible directions. And in average, you don't have any current. But if you apply the electric field, you shift your Fermi surface out of equilibrium, and now you have more electrons moving to the right than to the left. And this discrepancy gives you some current flow. But in our experiment, and this shift typically characterized by so-called drift velocity, which is average velocity of electrons along the current direction. And in our experiments, we observed that if we try to estimate the drift velocity around the transition point, that it becomes comparable to the Fermi velocity of electrons in graphene. And that corresponds to quite an unusual situation. The condition that drift velocity equal to the Fermi velocity correspond to the moment when all electrons in your conduction band actually move at the same direction. And you don't have electrons moving in opposite direction anymore. And under this condition, we observe the peaks in differential resistivity, which converge to the neutrality point. If you try to model the electron transport in the presence of just single band, you immediately see that differential resistivity starts to diverge, and that's exactly what we see at our experiment, diverging differential resistivity before we reach this point. But in our experiments, we clearly can go further, and that's possible only if electric field starts to borrow electrons from the valence band and move them to the conduction band, and you create electron-hole pairs. And this process actually is a direct analogy of so-called Schwinger electron-positron creation in a vacuum, which was predicted in 1950s. But in real space, to observe this effect, you need to apply enormously high electric field, which was never done in experiment before, because this process have a gap in real space equals 2mc squared. But in graphene, you don't have any gap. So if you try to bias, and if you will use correct geometry, that's the main effect which you will see there, the creation of electrons and holes. Okay, and now with this understanding, we also developed a toy model to describe this effect and to describe the current propagation in this strongly out of equilibrium regime when electric field generates new additional carriers. And in this regime, you need to count that your particle creation rate should be compensated by the particle annihilation rate at the equilibrium, at the new equilibrium situation. And if you do so, you can show that if you try to source current beyond this transition point, the differential resistivity actually should drop as a function of current, and that's exactly what we see in our experiment. And that's exactly what our transition is, the transition from the Fermi liquid to the Dirac plasma region. Okay, here I need to generalize our effect and say that qualitatively our understanding stands the same, that this process is the same in pristine graphene and in graphene superlattices, like twisted bilayer graphene or graphene aligned with hexagonal boron nitride. But quantitatively, there is some difference there. And actually, if you try to estimate drift velocities in graphene superlattices, you will see a lot of difficulties because of very complicated band structure there. Qualitatively, physics is the same. The initial growth of the resistivity corresponds to the Fermi liquid regime and the tilt of the Fermi surface, and the further point corresponds to the moment of the creation of additional electron-positron pairs and creation of Dirac plasma. And with this in mind, that is the main recipe to observe those criticalities. If you have a system with a relatively small Fermi velocity and small Carrier density, and if you will try to increase the current there, you immediately should observe criticalities. Okay, moving a little bit further, we also did some experiments in other graphene-based superlattices like bilayer graphene or monolayer bilayer graphene. And at this point, I can tell you that it's very general process, and you basically will see those criticalities everywhere at this point. And recently, other people, like from Jeannie Lau's group, utilized the same approach and the same estimations to see to study the superconductivity in magic angle twisted bilayer graphene devices. And at this point, they claim that the critical current in magic angle twisted bilayer graphene is also limited by the similar out of equilibrium physics which we described in our work. All right, and here I'd like to stop, and thank you all for your attention.